The next speaker is Professor Ulf Hanefeld from TU Delft, and the title of his talk is Metal, Mobile or Stationary to Enable Catalysis. Ulf.
Thank you very much. And when I add something, Jim always wore these glasses. And I can remember when I joined the lab, he had one of his eyes lasered. And one of the glasses was therefore missing. And we went to a conference, I think it was in Durham. And Jim stood there in front of an audience like this. And he said, some of you might have noticed that I didn't recognize you. I apologize for this, but the glass is missing. And then he took the sticker. And I think that very much also characterizes him. Do I, by the way, need a microphone?
Oh, yes, I must give you that. I'm slow. Sorry about that.
Okay, so it is now pretty exactly 30 years ago that I joined the University of Cambridge. And I came to a beautiful university, I think we can all agree, with a town attached to it. And from Cambridge, I moved to Delft, which is a beautiful town, painted here by Johannes Vermeer, but it still looks as beautiful, with a university attached to it. And there we do some, what I think, interesting research, and I'd like to share some of this. But before I do this, I would like to thank the organizers of this conference for doing this. I think this is an absolutely marvelous tribute to Jim. And I'd like to thank Jim for sharing his knowledge with us, but in particular, his smile and his laughter. So today I'd like to have a look at metals, and then metals in enzymes, so metalloenzymes. And I would like to address the fact whether they are actually mobile or stationary. And commonly we look at a metal as something fixed, and then everything else is happening around it, just like we often do in life. We are fixed, the rest is moving around us, or the sun is fixed, the rest is moving around us. So what about the metal? Is it really fixed? How does it move around? And we all started this when we wanted to prepare this type of compound. We wanted to set up these two stereo centers, and retrosynthetic analysis says that you should use hydroxypyruvate and an aldehyde. And here in Cambridge, I've done lots of aldol chemistry with Jim, and we used a lot the chiral boron enolate. And I saw Ian Patterson a few minutes ago. Yes, the chiral boron enolate was something I've often heard you talk about. And so we applied this a lot, and we thought, let's do an aldol reaction here as well, but don't use a chiral boron enolate, but rather use an enzyme to become a bit more environmentally friendly, just as Rich explained to us before lunch. So if you then look at the enzymes that catalyze an aldol reaction, that are the aldolases, there are 4 of them, and they're grouped by the donor. At least that's how the biochemists call it. Chemists call it the nucleophile. So there are 4 nucleophiles that these enzymes use, either pyruvate, acetaldehyde, dihydroxyacetone phosphate, or this glycine. And if you look at that, then this is pretty similar to the substrate we wanted to use. So we were wondering whether there are some of these enzymes around that can use hydroxypyruvate. And fortunate for us, a French group had then just done the research for us, and they had published a number of enzymes that do this. So they found that you had a number of metal-dependent aldolases, so class 2 aldolases, that can utilize hydroxypyruvate. And you have 2 different enzymes that are particularly successful. That is the sphingommonas one and the Burkholderia one. And they always set up the stereochemistry here in exactly the same way. And the sphingommonas one gives you the OH pointing backwards, and the Burkholderia one gives you the OH pointing forwards. So we had found this, and we wanted to know more about it. And this is now pure coincidence, but today I walked into Tim Bugg, and I didn't know that he would be here at the conference, but this is a slide or a picture from him out of a paper he published a number of years ago where they characterized this type of enzymes. But here with pyruvate and not hydroxypyruvate. And you can see the pyruvate coordinates to a divalent metal. you, via a histidine, deprotonate, and you make your enolate. And this is the equivalent to the chiral boron enolate. And then we've got an arginine that coordinates the aldehyde, and then you do the chiral CC bond formation, which is what we wanted to do. But there were a few differences. We had new enzymes, so we wanted to know which metal. The hydroxypyruvic acid has a hydroxy group which can also coordinate to the metal. So how does it coordinate? And is it also arginine and histidine that is important in our enzymes? So first of all, the metal analysis. We did a retroaldol reactions as an activity assay, and then you can reduce here and you can follow this in a photospectrometer. And we saw that for both of them, manganese and magnesium are the favored metals. That's pretty much what I just showed to you before. We then took the manganese. Manganese 2 plus is EPR active, so you can follow in an EPR whether a substrate coordinates or not. And this is the control of the manganese, and this is the enzyme with manganese. And you can see a beautiful sextet, what you expect for manganese. And if you add pyruvate, you can see a change. And if you subtract, then you can see here this new spectrum that we get for the coordination. And for both enzymes, we get very similar spectra. So pyruvate clearly coordinates. For hydroxypyruvate, we also see this, however, a little less pronounced. So they seem to coordinate in a similar manner. And we then also did X-ray structures. And in the X-ray structures, we found, yes, indeed, hydroxypyruvate coordinates just like the pyruvate does. So we've got our metal here. We've got the acid group, the keto group of the hydroxypyruvate. And we've got an acidic residue of the enzyme and another acidic residue coordinating the enzyme. The metal, sorry, and then we've got two water molecules coordinated to the metal. And for the other enzyme, we also crystallized that, and you see exactly the same situation. Metal here, divalent bidentate ligand, and one acidic residue, second acidic residue. And if you overlay the X-ray structures, you can see that in essence, it's the same in both enzymes. What is remarkable here is that we also found the reason why these enzymes accept hydroxypyruvate. And that is they have this phenylalanine here. And this phenylalanine forms pi interactions with the hydroxy groups, which enables the enzyme to utilize not only pyruvate, but also hydroxypyruvate. So we found out a little bit extra now. The phenylalanine is important, and for the rest, everything up to now was exactly as Tim had published earlier. Good. So what about this arginine? And when you mutate it away, you lose all activity, and then we managed in a soaking experiment to get our hydroxypyruvate into the active site, and also an aldehyde, and this is the carbonyl group. And you can see that nicely coordinates to the arginine, and if you mutate away the histidine, you lose the base and nothing happens anymore. And overall in this reaction, this enolate, made chiral by the scaffold of the enzyme, determines the stereocenter at C3, and the coordination of this aldehyde determines the stereocenter at C4. And this is then the picture for the chemist, and since I'm still a chemist, I quite like to draw these pictures. So we've got the coordinated pyruvate, we deprotonate, we get our chiral enolate. And then we get the nucleophilic attack on the aldehyde, either like this or like that, and depending on which way around, the stereocenter here is different. The stereocenter here is always the same as both enzymes coordinate the hydroxypyruvate in exactly the same way. When we performed these experiments, we noticed that the stereochemistry here during the course of the reaction changed for both enzymes. And we were a bit surprised about it. Now, in general, if you perform a reaction and you catalyze it, then you know that in principle only the activation energy should matter because the catalyst lowers one activation energy and doesn't lower the other one. In the case of diastereoisomers, so in case of enantiomers, both have exactly the same thermodynamic stability, but if you make diastereoisomers, which we are doing here, one diastereoisomer is typically more stable than the other one. So if this reaction occurs, and you have an enzyme forming this diastereoisomer, it lowers the activation barrier here, and you get this. Very simple. If it's the other way around, it lowers this activation barrier, you get this product. But, and this seems to be the case for us, and it has been described for other enzymes earlier, you have some cases where this activation barrier is not that different to this one. So the enzyme actually enables both reactions, only this one is fast and this one is slow. So you initially form, in the fast part, this, but if you leave it, because you're going for lunch or whatever, your DE changes and you get this. So overall, your diastereoselectivity is actually determined by thermodynamics and not by the selectivity of the enzyme. And you only see the selectivity in the initial stage. So what you basically have is that this is your thermodynamic distribution of the diastereoisomers, and your enzyme might be initially selective for one of them, but over the time it always goes to equilibrium. And that is what we observed for these enzymes. And yesterday evening, I was fortunate to get a new X-ray structure from our collaborator. And what you can see here is that the hydroxypyruvate is nicely coordinated. But here in a soaking experiment, we found that the aldehyde was in part of the crystals coordinated in one manner and in part in the other, resembling this or showing this lack of selectivity for stereocenter at C4. So via X-ray crystallography proof. Okay, so up to now, this is, let's say, a little bit special, but not that unusual yet. When we then tested different buffers, we found that one of these two enzymes is activated a lot by a phosphate buffer, while the other one isn't. pH optimum, both of them are between 6 and 7, so that's not really much of a difference. But one of them is phosphate activated, and the other one isn't. And this has been described in the literature before for these aldolases, that some people say, no, they're phosphate activated, and others say they are not. And obviously we had here two enzymes, each with one of these properties. So we had a good look at it. And the first thing we double checked is whether it's a pH influence thing. So we took a buffer, not phosphate, to set the pH and just added a little bit of phosphate. And you can see that we have the same effect whether there's buffer and phosphate or only phosphate. And if you go up in phosphate concentration, you lose activity because then your metal precipitates as a metal phosphate, which is insoluble. Okay, so to further understand this, we looked at the entire kinetics, and the first step is the deprotonation. And this you can easily follow by HD exchange in an NMR. And when we did this, we found that for the enzyme, which is phosphate activated, this deprotonation is 120-fold faster than in the absence of phosphate, which was in good accordance with the literature where it was 150 times faster. And we also looked at the retroaldol reaction again, and even there we found a 10-fold increase in rate by phosphate. For the other enzyme, this was not the case. So we then did soaking experiments with our crystals, and we did soaking experiments for 2 years, and we never succeeded to get the phosphate into the active site. So we finally did then a modeling study where we put the phosphate via modeling into the active site, and you can see that the phosphate then sits in a position where it's ideal to aid the deprotonation of this hydroxypyruvate. And for the other enzyme, if you do an overlay of the structures, you can see that the backbone that is here in salmon is in green, and that is in the same position as that phosphate, so the phosphate activation would not be possible in this enzyme. So we now think we have a good explanation why some enzymes are phosphate activated and others are not. So to summarize at this point of my talk, we know which metal is used, manganese or magnesium, a divalent metal, a Lewis acid. The hydroxypyruvic acid is coordinated just like pyruvate. The arginine is essential, as it had been published before. It's again histidine as a base. For the diastereoselectivity, we found a good reason why C4 is not perfectly controlled, because the aldehyde can dock in two different manners in the active site. And then, of course, the nucleophile will attack from the different sides. And we have found, hopefully, the reason why phosphate can be a cofactor in one enzyme and is not a cofactor in the other one. So what about other structural details? When we did our X-ray structures, we noticed that the enzyme is a classical TIM barrel structure. And what you can see is that it has got one of the alpha helices pointing out rather than being in this position where it should be. And this is because in a domain swap dimer, that alpha helix then goes into exactly the right position for the other TIM barrel. And that makes this a very stable dimer. And that's also quite commonly found in biochemistry. So we've got domain swap dimers, and for both enzymes this is the same. And then these dimers form trimers. So overall we have a hexamer. And you can see all the 6 colors there. And in this hexamer, you can see that we've got the metals of the active site. In here you can also see the hydroxy pyruvate sitting there, and you should be able to see it there. Whether we could make a little puzzle whether you can see all 6 of them. And we delay this, but I'm sure Alison can incorporate that into some nice game. Now the active site is not inside one of these monomers, but it's actually at the interface of 2 of the monomers, and then not for the domain swapped monomer. So that's not at that position. So we've got the active site here with the metal. These are the 2 acidic residues that coordinate the metal, and this is the hydroxy pyruvate. And that is the other subunit being close by. And when we examined all of these structures carefully, by then we had assembled something like 10 different X-ray structures, we found that indeed this is nice in this position. And we then also looked at the structure again closely at a very high resolution in the absence of hydroxypyruvate. And what you then notice is that all of a sudden this serine of the other side chain is coordinated, while the rest of the structure didn't change. So the metal must have moved from here to there. So we've got 2 residues, 2 acidic residues that coordinate the metal. And then when there's no hydroxypyruvate as bidentate ligand, that metal shifts over here and there's a serine there coordinating it. And if you look at that and do an overlay of the structure, you can see that the protein in essence doesn't move. So we've got these 2 acidic residues in gray and in blue. They're more or less in the same position. And in one case, this serine OH coordinates the metal. And when there's hydroxypyruvate present, the metal shifts by 2.4 angstroms into a different position, and that is the reactive position. So we have a resting state and an active state. And when we then went through all of the X-ray structures we had determined and had either manganese or magnesium in there, we even found a 3rd position, and this is where we have a pentacoordinated metal, where you have a square plane here and this one point. So this is a nice Egyptian pyramid. And we looked at this in terms of stabilities and did quantum mechanical calculations in order to see whether this made any sense. And we set this as 0. And what you can then see is that this transition state, or this movement, does make sense. This is a bit more stable, while if it's hexa-coordinated, it is less stable. And this is indeed the most stable state for the metal, so coordinated with the dihydroxyacetone phosphate or with the hydroxypyruvate. Okay, so we then thought perhaps this movement takes place because it keeps the dimer together. The serine, as an additional ligand, stabilizes the structure, and we looked at the melting temperature of the protein, and we took the wild type and we made a mutant where we replaced serine with alanine and also serine with cysteine. This one didn't produce easily, and it also didn't crystallize. The other one did crystallize, and they had the same stability. If you add the metal, all of them become more stable, and if you add the hydroxypyruvate, all of them show exactly the same stability. So we can conclude that this serine does not help to stabilize our protein, and it does not influence the thermal stability of this enzyme. So the dissociation of the enzyme does not take place via that dimer falling apart. So what we propose, but that has to be shown, is that this is actually a mechanism that ensures that the metal doesn't leach out of the enzyme when the enzyme is not catalytically active. Good, so what about the other enzyme? Is this the same, or is here again something different? So I showed earlier that if you overlaid the two enzymes with hydroxypyruvate in there, it's essentially the same. We then overlaid the two structures in the presence of the metal, but without hydroxypyruvate, which caused that metal movement in one of them. And the orange one is the one where we saw this big movement, and this is this serine that is coordinated, and these are the two acidic residues. And you can see this is the green backbone for the other enzyme. There is no serine, so there can be no coordination, and the metal is indeed not in the same position. It's just coordinated by these two acidic residues. And there's a difference in position of roughly 1.2 angstrom. What about this BPHKA then in the presence and absence of hydroxypyruvate? And here you can see that the protein structure doesn't change at all. So this is exactly on top of each other. This is without the hydroxypyruvate. This is with the hydroxypyruvate. So we see a shift of the metal by 1.4 angstroms due to the coordination of this divalent ligand. So to come to my conclusions, for one of our two enzymes, we really have two distinct metal binding sites. And they are 2.4 angstroms apart, and we have a shift upon coordination of the substrate. And it's the metal that moves and the protein doesn't. For the BPHKA, we only have one metal binding site. There's a small movement of the metal upon coordination of the substrate. And again, it's the metal that moves, and it's the protein that doesn't move. And of course, then you can think, is this unique? And that's, of course, also something we asked ourselves. So we did a thorough literature research. And my conclusion is that metals in metalloenzymes are not static. The number of examples is relatively limited. But I also think that many X-ray structures are not at the resolution of 1.5 or 1.8, what you really need to see this, but at 2.5, and then you don't really see this shift. So I think it's a good idea for any one of you, or anyone in general, working with metalloenzymes, to have a good look at the structures, whether there's actually a shift of the metal. And I personally think this must be a bit more common than we think up to now. And we summarized everything that we found on this in this review recently. So if you want to read more on metal movements, you can find that there. I now come to the nicest part of my talk, which is the acknowledgements. First of all, of course, want to acknowledge Jim as someone who inspired all of us, and also me in Delft. And I'd like to thank all the people that did the work, in particular Stefan, who started it, together with Sander and Afina, who then finished off everything. Laura supported the biochemical work, and Peter Leon did all the EPR work. Isabel was so kind to send me the X-ray structure yesterday evening, and Hein did the work on the quantum mechanical calculations. And I'd like to thank the entire group in Delft for the good working atmosphere and at making it fun to go to work every day. And I'd like to thank you for your kind attention.
Thank you all for answering the question you posed in the title of your talk.
Yeah, so you don't have to ask it anymore now, but you're allowed to ask other questions.
No, the good questions asked it.
Yeah.
So, I want to just add, because I forgot, thank you very much.
Yeah. Yeah.